Hello students, welcome to the next lecture on the sequence. Today we will describe the non-decreasing sequence theorem. I will explain this with the help of the 8 examples. Myself Dr. Harish Garg. You can simply follow my YouTube channel for various videos on sequence and series. So as we defined in the last lecture, what is a sequence? A sequence is a function whose domain is a set of the natural number and range is my real number. So we have also defined several examples in our last lecture. So few of them are listed here, which is the infinite sequence. Again, you can see this is the infinite sequence, and here the sequence is denoted by curly braces, or the sequence is denoted by here. There are the three different kind of the sequences. One is called as a convergent sequence, divergent sequence, and oscillating sequence. How you can find the sequence, how you can prove that the sequence is convergent or not? We will find the limit of this sequence an as n approaches infinity. If this limit is my finite and unique, then we can say this is my convergent sequence. If this limit exists and finite, we can say this is the convergent. On the other hand, if this limit does not exist and it's a plus infinity or minus infinity, then the sequence is called as divergent. While the sequence which is neither the convergent nor the divergent is called as oscillating sequence. A very simple example is my here. So you can see the previous lecture of the sequence and its examples for various detail. How you can check about the sequence? As I mentioned in our last lecture, there are the two methods. The first method, as I explained you here, if the limit goes to the L, which is a finite and unique, then it's a convergent, otherwise not. This method, the various examples related to this method I already explained in our last lecture. Now in this lecture we will explain you the second method. When you can say the sequence is convergent, it is if and only if. That is, if you prove that the sequence is a non-decreasing, or what is the meaning of the non-decreasing means, if you prove that sequence is by increasing and sequence is a bounded above, then you can say the sequence is convergent and it converges to the least upper bound. How we can find the least upper bound, that we will see in this couple of examples. So this is the objective of this today's lecture. So what is the non-decreasing sequence theorem? That is, any of the sequence an is said to be convergent if your sequence an is a non-decreasing or called as increasing and the sequence is my bounded above. Remember, this is the if and only if. Means if you have the sequence of the non-decreasing plus it is bounded above, then it implies it is convergent. On the other hand, if you prove that the sequence is a non-decreasing plus it is a convergent, it implies it is bounded above. So that's the meaning of if and only if. How you can prove the non-decreasing sequence or the increasing sequence? We will start with the an plus 1 minus of an, and our target is to prove it is a greater than 0. Then the sequence an is said to be the monotonically increasing or monotonically non-decreasing. How you prove that sequence is a bounded above? We can find a number which is, we can find a real number m such that the sequence is less than of this. For example, if I consider 1 by n, here n is my natural number, then we all know 1 by n is always less than 1. So it means this number is my m is my 1. So if you want to find more examples and detailed study about the monotonic sequence and the bounded above, I see you can watch my previous lecture. This is the first lecture we already covered, monotonic sequence and the bounded sequence. You can see more than 15 examples in each lecture. Remember that if the monotonic, if it's a non-sequence converges, then it converges to the upper bound. How you can find the upper bound, that we will see in the couple of examples. So for example, here you have to test the convergence and divergence of this sequence. If I apply the first method on this, what will be the result? That means you have to apply limit n approaches infinity of this. So what is the answer of this? If you apply this limit n plus 1 over n plus 1, so clearly say it's an infinity by infinity form. So you can apply the L'Hopital rule, or you can divide it by n on the both sides. So the answer is 5, which is a finite and unique. So therefore this sequence is my convergent and it converges to the 5 limit, and this 5 is my upper limit. Now, but in the question suggested you have to find the convergent by using this theorem. What is the theorem is? You have to prove that this sequence is my monotonically decreasing, or sorry, monotonically non-decreasing and bounded above. A very simple approach. We can start from here. What is the an plus 1? I have replaced n to be n plus 1. Fine. Minus of an. This is my an. So what is that? This is 5n plus 6 divided by n plus 2. Now you can take the LCM. You will get this expression. Now if you open them, it will be cancelled. This will be cancelled. So the remaining expression will be here. Now your target is to prove that it is a greater than 0. So since n is my natural number, so what is the meaning of the natural number is n is my greater than equal to 1 and a positive number. So can you identify that whether this term is always positive? Is it always positive for each n? Yes, this is always positive. So this means it is always be greater than or equal to 0 for all n. Hence the sequence is monotonically increasing or monotonically non-decreasing. So the first property is satisfied. How you can prove the bounded above? So your target is to start with the an and your target is to find the value of less than equal to something. Fine. How you can find? Again, a very simple. You can see the degree of numerator and degree of denominator are same. So you can simply either divide them, or I can make this n to be n plus 1. So I have to minus 5 plus 1 so that I can cancel out this. So this becomes a minus of 4. Now if you separate them, it is 5 minus 4 over n plus 1. Fine. Now you all know if x and y both are my positive numbers, then x minus y is always less than of the x and x plus y is always greater than of the x. Fine. If the equality is there, then you can write also as the equality. Now you can see this number, since n is my greater than equal to 1 and a positive number, so what is the meaning of that? This number is my always positive. Fine. 5 is also positive, so difference is always less than or equal to 5 or only 5. So you can see this is less than 5 for all n. So we can find a m, so therefore sequence is bounded above by 5. So both the properties are satisfied, hence the sequence is convergent by using non-decreasing sequence theorem. And once it is here, then how you can find the limit? Limit is always be my here. So the limit is 5 is the right answer. There is one more method you can check about the bounded. There is one more method how you can check about the bounded above. So for that, if the first thing is you have to prove that it's a non-decreasing sequence and you can find the limit. If this limit is my finite and unique, then you can directly write as an is less than, equal to or only less than n. Make sure the only this condition does not mean that it is bounded by above until or unless you prove that it is a non-decreasing. For example, I come back to this, since I already proved that it's a non-decreasing, so what I can do, I can simply find the limit of this. So what is the limit of this? You can easily see it's an infinity by infinity form, or I can simply divide numerator and denominator by n. So the answer is 5. So you can see which is a finite and unique. So what is the meaning of that? This an is bounded by above by 5. So this means because an is my non-decreasing, limit is my finite and unique, so therefore sequence is less than 5 for all n. You can also check that what is the a1. You can see what is the a1 is 6 over 2. It is a 3 which is less than 5. You can find a2. a2 is my 11 over 3. 11 over 3 which is 3 point something, again less than 5. You may take any of the numbers, say 101. What is the 101 is? It's a 506 divided by 102, which is again less than of the 5, and so on. So each number is less than 5. So hence the sequence is bounded above by 5. So we can say the sequence is convergent and the limit is my this answer. Now look at the second example. You have to check whether the sequence is a non-decreasing and bounded above. So that is a non-decreasing sequence theorem. So what is the an plus 1? We can find here. I can change here. Take the LCM, which comes to be here. These two values are cancelled out. It's come to be this number. Now clearly says because n is my greater than equal to 1 and always a positive number, so this number is always be greater than 0 for all n. If you take as n is infinity, then it's a equality also be there. So therefore this sequence is my monotonically increasing. How you can find the bound? So that there are the two, because you already proved that it's a non-decreasing, so you can simply find the limit of an is my L, then an will be less than of the L is there. Otherwise your target is to prove this number is less than of something. Again, the degree of the numerator and denominator are same, so I can replace this n to be the n plus 1. So I have plus 3, I can subtract minus of 3 also. Now you can see the numerator part will be the minus of 2. I can separate them. Again, this number is my always a positive number, so 3 minus something is always less than of 3. Hence sequence is bounded above by 3. Or another method how you can check about the bounded above, because it is a monotonically decreasing, monotonically non-decreasing, so we can found the limit of an. So what is the limit of an as n approaches infinity? So this is nothing but my 3. Since it's a non-decreasing, its limit is finite and unique. This is finite and unique. So what is the meaning of that? This is bounded above by 3. So you can apply either of the way. Hence the sequence is convergent and the limit is my 3 is my limit. Look at the another one. You can see now this is the factorial. Again you have to check whether it's a non-decreasing or not. So we can start from here. What is the an plus 1? So it is nothing but 2n plus 1 plus 3 of factorial divided by n plus 1 of 1 factorial minus of this. So you can write here. So what you can do, I can simply expand the numerator firstly. 2n plus 1, 2n plus 5, 2n plus 4, 2n plus 3 factorial divided by n plus 2 and n plus 1 factorial minus 2n plus 3 factorial over n plus 1 factorial. Now I can take 2n plus 3 factorial over n plus 1 factorial common. What is the remaining side? The remaining side becomes here. Now you can take the LCM, which comes to be this. You can simplify this 18 and minus 9 is 17 and so on. Again, n is my greater than equal to 1, which are the positive numbers. So each term is my positive. So this number is my greater than 0 for all the values of the n. Hence, this is my monotonically decreasing. How you can prove the bounded? So you can see about here. So your target is to find the limit of this. So since it's a factorial, so I can open this numerator part. So it's a 2n plus 3, then 2n plus 2, then 2n plus 1 and so on up to n plus 2, n plus 1 factorial divided by n plus 1 factorial. Now you can see this number will be cancelled out, so the remaining expression will be here. So can you say this number is less than of something where n is my greater than equal to 1? You can't say that, because if you take n is my 7, then you will get some number. If you get n is 8, then you can different number which is not less than of this number. So what is the meaning of that? If it is not less than, it is not bounded above. So once the one property is not satisfied, so therefore the sequence is not convergent. So that means it is a divergent sequence. Or otherwise you can also prove that like of this limit n approaches in, because you already proved it's a non-decreasing, so you can start from here. So what is the limit of this? 2n plus 3 factorial over n plus 1 factorial. So again you can see after that you will get here what is the limit of this as n approaches infinity, which is infinity, which is not finite. If it is not finite, it means this is a divergent sequence. Remember that once you are proving here, if the sequence is not monotonically increasing or not, then you can't apply this test. If either of these condition is not satisfied, then you can't apply this one, or most precisely, if this condition is not satisfied, then you are unable to apply this non-decreasing sequence test. Fine. Then in that case you have to apply the type 1 for that. For example, here you can see, if I consider this sequence is also be written like of, I can combine them 6 raised to power n over n factorial. That's the same thing. Fine. So firstly we can check whether it's a monotonic or not. We can start from here. I can take 2 raised to power n, 3 raised to power n over n factorial common. So what is that? It's a 2 into 3 divided by n plus 1 minus of 1. So after that you can take the LCM, which comes to be here. Is it always be greater than 0 for all n? Is it always be? No, because if you take n is 7, this numerator part is a negative and the rest all the terms are positive. So when this is 7, then this number is less than 0. So what you can say, it means this is greater than 0 only when n is less than or equal to 5. So if I take equality 5, then it's a 0. So it means, what is the meaning of that? This is increasing only for this one, but you have the infinitely many terms. This is the infinite sequence. Fine. So it means you have a1, a2, a5. This is my non-decreasing, while a6 to a infinity, it is my decreasing sequence. So what is the meaning of that? It means this sequence is not non-decreasing. So that means the sequence is not non-decreasing. Fine. So once the sequence is non-decreasing, it means we can't apply this non-decreasing sequence test. Fine. So it means how you can check the convergence and divergence, because we are unable to apply the test. It means we are unable to check whether it's a convergent or not. So another way is we can simply find the limits. If it is a finite and unique, then you can say it's a convergent or not. So what is that? This is limit n approaches infinity, 6 raised to power n over n factorial. So you know what is that? You can simply use the one formula which we already explained in our last lecture, which is for all x. Here x is my 6, which comes to be 0, which is finite and unique. So therefore this is my convergent sequence. Remember, if this is my convergent here, remember, if in this case, if my expression will be like of this, for example, if my this term will become to be here, then this is my greater than 0 whenever n is greater than equal to 5. Fine. So since majority of them, it means up to the a1 to a5 is not increasing, while the most of them a infinity, it's my non-decreasing. So then you can apply this test, because majority of them will satisfy this property, while in this example only the few values are satisfied but not the majority of them. Now once we know it's a convergence, so by using the non-decreasing sequence test, it has definitely a bound. So how you can find the bound? So remember, as if I apply the second method for finding the bound, which is to be here, but this is not the right meaning. It doesn't mean that 0 is the upper bound. Why? Because we already proved that this is not a non-decreasing. If it is a non-decreasing sequence, if we prove that it's a non-decreasing sequence for majority of the n, then this is the upper bound, but this is not true. Then how you can find that? So since an is a non-decreasing for this one, fine. So this definition we can apply only up to the 5. So that means we can find the value of the a at the upper bound, that's a 5. So what is that? If you solve this expression, it's come to be 64.8. So that means this sequence is bounded above by 64.8. Although this sequence is not non-decreasing, but it is a bounded above. How you can prove? You can see your sequence will be 2 raised to power n, 3 raised to power n over n factorial. What is the a1? a1 is my 6 over 1 factorial, 6, which is less than of 64.8. You can find a2. So 2 raised to power 2, 3 raised to power 2 over this one. So you can see, once you can compute, you can see this number is also 64.8, this number is also 64, each number is less than of the 64.8. Hence, the sequence is bounded above, but it is not monotonically non-decreasing. Look at one more example. Now sequence is given to you, so we can check for the monotonic firstly. So what is the an plus 1? It's a 2 over n plus 1, 2 over n plus 1. What is that? This is 2 minus 2 over n, 1 over 2 raised to power n. Now you can see that this 2 will be cancelled out. I can make the pair of 2n over this as 1 pair, minus minus plus 1 over 2 raised to power n and 1 over of this. Now you can take the LCM of this, you will get this expression. Now clearly says n is my greater than equal to 1, which is a positive, so this number is a greater than equal to 0 for all the values of the n. Hence it is a non-decreasing sequence. Once it's a non-decreasing, then you can apply the bound. So how you can start the bound? Your target is to find this number should be less than of something. So again, as I use the same trick for you, if x and y are the positive numbers, this number will be less than of x. Or if now, in this case, there are the three numbers x, y, z. So you can say x minus y minus z must be less than of the x. So make sure these all numbers are my positive. So you can see this is my positive, this is always greater than 0, this is my always greater than 0. Why? Because n is my greater than equal to 1. So you can say this number is less than of 2. So hence it is bounded above by 2. Otherwise, second method is, since it is a non-decreasing sequence, so how you can find the sequence which is bounded above? We can simply find the limit of an as n approaches infinity. So what is the limit of the an? This part goes to the 0, this part goes to the 0. So this value 2 minus 0 minus 0, that's a 2. So therefore sequence is bounded above by this limit. So that is bounded above by 2. So that's on your choice whether you want to use this or this one. Now sequence is non-decreasing, sequence is bounded, both conditions satisfied. So by the non-decreasing sequence theorem, sequence is convergent. And what is the convergent limit? So limit is my 2 is my convergent limit. Now look at this another one. You can clearly say whether it's a decreasing or not. You can start with the n plus 1 minus of this value. Now if you open this bracket, you will get this simplified expression. Now clearly says n is my positive number, natural number, so this is a greater than 0, hence it is a non-decreasing. How you can prove it's a bounded? You can start from here. Target is to find this number. Since this number is always my positive number, so this is my less than of 1. Hence it is bounded above. Or second method, since you already proved that it's a non-decreasing, then limit n approaches infinity of an. So what is that? It's a 1 minus 0, 1. So therefore your an is less than of 1 is my upper bound. Make sure if it is a non-decreasing, if this condition is not satisfied, then you can't apply this method. This method is applicable only when you prove that it's a monotonically increasing. So hence by this theorem, the sequence satisfies both the properties, so it's a convergent and the limit is my 1. Look at one more example. So again you have to firstly check about the monotonic. You can start with this. Now you can see 1 will be cancelled out. You can take the LCM of this, you can find this expression which comes to be here. Now clearly says this number is my positive, so 1 plus, now here you can see x and y is my greater than 0, then x plus y must be greater than of the x. So clearly say 1 plus x, it's always a number, is positive, because this number is positive, this is positive, so sum will also here positive. Now since this condition satisfied, so you can find the bounded above by either of the method. So if I start with the second method firstly, what is the limit n approaches of this? So can you find the limit of this part? What is that limit of this? It comes to be infinite, because this part is my 0, which is not finite. So what is the meaning of that? This means this sequence is not bounded above. Fine. So this sequence is not bounded above. So since this property is satisfied but this property is not satisfied, so this sequence is my divergent sequence. Fine. This is the first method. Second method is, you can start with here. So since this number is a positive, this is a positive, so it is less than of the n, but n is my not fixed number. N is my not fixed. If you take n is my 7, then it is less than 7. If somebody take n is 9, it is less than 9. So this number is not particularly well defined. So hence this number is my as large as possible, that's infinite. Sequence is unbounded. So once it's unbounded, so this property is satisfied, this is not satisfied. So by this theorem, the sequence is my divergent. Once you see divergent, then you are unable to find the limit. Look at the one more example. So now this is the sequence of this. First of all, you can simplify this. I can write this sequence like of this one, so that it will become easier than. Fine. Now we can start from here. Fine. This is the an plus 1. It will be cancelled out. So 1 over 2 raised to power n, 1 over 2 raised to power n plus 1. I can take 1 raised to power 2n is a common. It is 1 minus 1 over 2. So what is that? It is 1 over 2 raised to power n into 1 over 2. I can written as 2 of n plus 1. So this number is always a positive because n is my natural number. Hence this property satisfied. You can find the bound. Firstly here your target is to find this number. I always prefer to check by this method. So because this number is my positive, so this number is always less than of 1. Otherwise, because you already proved that it's increasing, so you can find the limit of an as n approaches infinity. So what is that? This is 1 minus 1 over 2 raised to power n. So what is the answer of this? This part will goes to the 0. 1 minus 0 is 1, which is finite and unique. So therefore you can say, because an is my monotonically increasing, so this number is less than of 1 for all the values of the n. So since both the properties satisfied, you can say the sequence is my convergent and the limit is my upper. So this is called as upper bound limit. This is my upper. Fine. So I hope you can simply learn the various tricks for solving such kind of the problems. We will see the next lecture on the Cauchy first theorem of the limits. Till then, you can simply like, share and comments on my video. Best of luck students. Happy learning.